Everyone, and welcome to today's edition of the Extremal and Probabilistic Combinatorics seminar. Uh, Before we start, let me go through the usual technical stuff. So this talk is being recorded, and we will post it on YouTube later on. So please bear that in mind in case you want to ask questions. There will be some time at the end after the talk. There will be space to ask questions even in the unrecorded mode. And our today's speaker has asked me to know that it might be that her webcam will stop working at some point. So, but
yeah, the video just might frizzle and go out. This is happening for a while with my laptop. So yeah.
But the slides will be the shared screen will be available, so that's and also in a minute or two I will try to arrange that you can get to her slides on our seminar webpage. So that's not available yet, but it will be available in a minute or two. And so now it's my pleasure to introduce Moumanti Podder from the New York University in Shanghai, and she will talk about some games on Galton-Watson trees. So please.
Thank you so much for that, Honza. I'm very honored to be here. I just wanted to say at the very beginning that I'm recovering from probably COVID, which means that I have like a bad cough, and this might just punctuate the talk. So it's annoying, and I apologize at the very beginning for that. Okay, so this work, which is ongoing, and I'm trying to wrap this up in like the next couple of months, is inspired by this paper. So I'll just exit the full screen and I'll show you the paper. So this paper is by Ander Holroyd, who's one of my collaborators, and James Martin, which talks about Galton-Watson games. So, and I'll just go back to, and this came out in, okay, this got archived in 2019. So I'm not sure when it came out or if it has come out at all yet or not. Okay, so Galton-Watson branching processes. So this is a pretty well-known stochastic process, which was proposed by Francis Galton, and it was Henry Watson. And it's the first purpose of this, proposing this model, this stochastic process model, was to model the ancestral family lines or family trees of the UK. But this gets used in a number of other applications, like spreading of infection and rumor and all of that. So in a rooted Galton-Watson tree, which is what we are looking at here, you begin with the root. So I will always denote the root in my talk by this letter phi. So the phi is allowed to have a random number of children, and this random number follows a certain distribution, which is known as the offspring distribution. Now, given that phi ends up having any child at all, each of these children, in turn, independently, has a random number of children of their own. And again, each of this is distributed according to the offspring distribution that I mentioned previously. And this is how you continue generating the tree. Now, I am looking at multi-type Galton-Watson trees, which is a little more generalized. So there is the concept of color or type of vertices involved. Now, in general, you will have a fixed set of colors, a fixed finite set of colors. And the paper that I'm working on has a general study of this. But for the sake of this talk, I will just focus on two colors, blue and red. Sigma sub v for any vertex v will denote the color of the vertex v, so it's either blue or red. So again, you have the root phi. You begin with the root phi, and you assign it the color blue with probability sum p, and color red with probability 1 minus p. So p is some given parameter. And then when you start generating the tree, again, the basic structure of Galton-Watson trees remains the same. However, now the offspring distribution will depend on the color of the parent vertex. So this means that conditioned on the color of V being blue, the probability that V has M blue children and N red children is given by chi sub B of M comma N. So this B here, the subscript B here indicates that you're looking at a blue parent vertex, okay? And this is going to be a bivariate distribution, obviously, because you're talking about the joint distribution of the number of red children and the number of blue children. Similarly, when you condition on the color of the vertex V being red, the probability that it has M blue and N red children is given by chi sub R of M comma N, okay? So you again end up with a random tree in the end. So let's denote that by script T. And the idea would be to visualize script T as a directed graph. How? So let's say that U is the parent of a vertex V. Then you consider the edge U comma V to be directed from U to V. Okay, so you always go from the parent to the child. Also, there are two kinds of edges that you can talk about here. One is monochromatic, which means that the parent and the child both have the same color, and non-monochromatic, where they have different colors. Okay, now the games that I consider, again, this is all inspired from Anders' paper with James Martin, and they also consider similar games. However, there is obviously a difference in the rules of the game. Okay, so let me first talk about the games that they consider. So all these games, the normal, misere, I'm not sure how to pronounce this, so if I'm pronouncing it wrong and if one of you know how to pronounce it, just let me know. So normal, misere, and escape, all of these games have two players, okay? And there is a token. So the token is placed at some starting vertex of the tree, and then the players take turns to move the token. So in their game, which is on the simple Galton-Watson tree, not multi-type, each player just moves the token from a parent vertex to a child vertex. And then in the next round, the next player moves the token from that child vertex to another vertex, which is a child of that child. You know, it just continues like this. And a player is unable to make a move when she arrives at a leaf vertex. Okay, but in my case, the game is different. So the game rules are as follows. So there are two players, P1 and P2. And P1 is allowed to move the token only along monochromatic edges. Okay, so that means that if the token is at a blue vertex, then, and if it's P1's turn to move, then P1 can move the token from that blue vertex to one of its blue children. Or if the token is at a red vertex and it's P1's turn to move, then P1 can move that token from the red vertex to one of its red children. And if, let's say, the blue vertex does not have any blue child, or the red vertex does not have any red child, then P1 cannot make a move. P1 gets stuck there. Similarly, P2 is allowed to move the token only along non-monochromatic edges. Okay, so that means that if the token is at a blue vertex and P2, it's P2's turn to move the token, and P2 can move it from the blue vertex to one of its red children. Or if the token is at a red vertex, then P2 can move it from that vertex to one of its blue children. Okay. So in the normal game, what is the rule for winning the game? So whoever fails to move the token loses the game. Okay. So if it is P2, let's say P2 loses the game. So either it is because P2 has reached a blue vertex that has no red child, or it has reached a red vertex that has no blue child, or it has reached a vertex that has no child at all. Okay. In case of misere games, this winning rule is just flipped, which means that whoever fails to move the token actually wins the game. Okay. Now, escape game, although I mentioned this here, I am not going to go into the details of this game. The reason is that this has a very different flavor from the other two games, because here there are two players, stopper and escaper. And the rule is as follows. So escaper is allowed to move the token along monochromatic edges. Stopper is allowed to move the token along non-monochromatic edges. I'm not sure if, so Honza, is the right side of the slide visible to everyone? Because, you know, I can see all of your faces.
Yes.
It's okay, okay. Yeah, because for me, it's like some of the text gets cut off a little bit, so that's why. But So how do we decide who wins the game? So if either of the players fails to make a move at any point of time, then stopper wins the game. Okay. And if neither of the players is ever, unable to make a move, so the game continues forever, then escaper wins the game. So in these two cases, in the case of normal games and misere games, there is the concept of a draw, because the game could potentially continue forever, in which case neither player wins. And so there you end up with a draw. But in case of the escape game, there is no concept of draw, because if the if the game continues forever, then escaper wins the game. Also, I assume this is the same as their paper as well, and I think this is standard assumption that in each of these games, both the players play optimally. So first of all, the tree is generated, and the realization of the random tree is available for both the players. They know what the tree looks like, and then they begin the game, and they play optimally in that if one player is going to win the game and the other player is going to lose the game, then the winner is going to try to win the game as quickly as possible, and the loser is going to try to prolong the game as much as possible. Okay. So I'll focus on normal and misere games. So let's look at the normal game. So how do we begin the analysis? So I will start by defining certain subsets of vertices of the tree. Okay, and I want you to pay special attention to the way I set up the notation, because it's kind of, because there are too many notations, and if I don't explain properly, this, it's going to be lost later on. So NW1B is a subset. I will describe how I go about, setting up this notation. So it's a subset of blue vertices V of the tree T, such that if you place the token at such a vertex V at the beginning of the game, and P1 plays the first round of the game, then P1 wins the game. Okay. So how did I set up this notation? First of all, this N indicates that we are looking at normal games. Okay. When we go to misere, we will replace this N by capital M. Okay. This first subscript here tells you which player plays the first round of the game. So 1 indicates that it is P1 who plays the first round of the game. This second subscript B tells you what the color of the vertex is. The color of the vertex where you first place the token, that color is blue if it's B, and it's red if it's R. And W tells you that the player who is beginning the game wins the game. Okay. So similarly, if you look at NW1R, then this is the set of all red vertices V, such that if you place the token at V at the beginning of the game, and P1, so again, you can see there is the 1 here in the subscript, in the first subscript. If P1 plays the first round of the game, then P1 wins the game. Okay. Similarly, when you go to NL1B, so here you can guess that L stands for loss, just as W stands for winning. So NL1B is the subset of all blue vertices of the tree, such that if you place the token at such a vertex at the beginning of the game, and P1 plays the first round of the game, then P1 loses the game. Okay. Similarly, you define NL1R. So likewise, you can define NW2B, NW2R, NL2B, and NL2R. So here I want to just remark that if you go to Ender's paper with Martin, you will see that they don't need to define so many subsets. They only need to define, the player who begins the game wins the game. The player who plays the second round of the game wins the game, and draw. That's all they need to define. The reason why I need to define all these subsets is because, unlike their situation, in my situation, the players' moves aren't symmetric. Because one player is moving along monochromatic edges, the other one is moving along non-monochromatic edges, and so you need to define all these subsets. Also, for each positive integer n, I define NW1B superscript n to be a subset of NW1B, such that if V is a vertex in this subset, then place the token at V, let P1 play the first round of the game, then P1 wins the game, but not only that, P1 wins the game in less than n rounds. Okay, so this is how I define NW1B superscript n. So this superscript will give you the upper bound on the number of rounds that need to be played for the game to conclude. Also, I set up this convention that NW1B0 is just the empty set, because of course it's not possible to define in less than 0 rounds what the outcome of the game is going to be. So likewise, you can define all the other corresponding subsets with these superscripts n. So this will sort of give you like a few, so 8 different sequences of subsets, and we will analyze those. Okay, so this is about defining the subsets. Now we define the probabilities. So again, this would be sort of self-explanatory. So I'm just, going from uppercase in the previous slide to lowercase here to denote the probabilities. So small NW1B superscript n is the probability that the root of the tree belongs to the class capital NW1B superscript n, conditioned on the root being blue. Okay. So I do prefer, I should say, not require, I prefer to have this conditional probability definition because it sort of makes my life simpler when I do the computations. In their paper, they had unconditional probabilities. Okay, so just mentioning that. Also, because of this convention that, we set capital NW1B superscript 0 to be equal to the empty set, and similarly for all the others. So that's why you have small NW1B superscript 0 to be equal to 0. Similarly, you define NW1 or superscript n to be the probability that the root belongs to the class capital NW1 or superscript n, conditioned on the root being red. Okay, and again, this when you replace the superscript by 0, you get 0 here. So likewise, you can define the other probabilities. So are the remaining 6 probabilities, and I've tried to color code this, depending on whether it's blue or red. And then you can also define in a similar manner the probabilities without the superscript. So NW1B, small NW1B is the probability that the root belongs to the class capital NW1B, conditioned on the root being blue. Okay. So this is how you define this. And if you have any question in the middle about, in case you forget the notations, please ask. Okay. So here is a small proposition that although we define all these sequences of subsets, we can show that if you look at this sequence, capital NW1B superscript n, this sequence actually increases to the set capital NW1B. Similarly, you can have the other relations. You can write down the other relations for the other subsets. And I just wanted to mention like a line of the proof, and simply using compactness arguments, where you look at this set. So this is NW1B minus the union of all the NW1B superscript n's. And you just show that this is going to be an empty set, because what does this set mean? So if a vertex belongs to this set, that means that if you, first of all, the vertex is blue, and that if you place the token at the vertex and let P1 play the first round of the game, then P1 wins the game, but cannot guarantee the win in any finite number of rounds. That's all this means. And all we have to show is that when that is the situation, when P2 is able to prolong the game indefinitely, she's actually able to guarantee that she's going to have a draw out of the game. And so P1 does not actually win the game, which means that this is going to be the empty set. Okay? So this is how you show the proof of this proposition. And as a consequence of this proposition, you also have that when you take the limit as n goes to infinity of these probabilities, small NW1B superscript n, this goes to NW1B. Okay, so this gives us, an idea about. So I will analyze things for these sequences and then take things to the limit as n goes to infinity, and then conclude things about, NW1B. That's the idea. And similar relations will hold for the other probability sequences. Okay. So here's, I just set down the notation for the probability generating functions for the offspring distributions, because this is going to be important for us later on. So G sub B gives you the PGF for the offspring distribution chi sub B. So if you recall, chi sub B is the offspring distribution of a vertex which is conditioned to be blue. Okay. And G sub R gives you the offspring distribution for, the PGF for the offspring distribution of a red vertex, okay? I also set down these notations. That is simply because, it's convenient, and it gives me sort of like it's for the sake of brevity, really. So GB superscript 1 of X, all this says is that it's going to be G sub B, X comma 1. So you're replacing Y, the Y that you see here, by 1. Okay. And the way to remember how I set up this notation is also hopefully simple. So GB superscript 1 of x, the superscript 1 tells you that x should be placed in the first coordinate and 1 should be placed in the second coordinate. So GB superscript 2 of x simply tells you that, again, you're considering G sub b, and that x should be placed in the second coordinate, 1 should be placed in the first coordinate. And similarly, you define these other two. So we will see in just the next slide why I define these extra notations. So the next slide is going to be about recursions. Okay, so I just tried to explain how I get two recursions. There are going to be 8 recursion relations, and the others are going to be very similar. Okay, so let's look at this recursion. So I consider a vertex V, which is in the class NW1B n plus 1. Okay, so what does this mean? This means that if you place the token at V, and if you let P1 play the first round of the game, then first of all, V has to be blue because you're considering NW1B. And if you place the token at V and let P1 play the first round of the game, then P1 wins the game because you have NW here. And she can win it in less than n plus 1 rounds. Okay, so this is what it means, just recalling things. And so for V to belong to NW1B n plus 1, what do you require? You require that the color of V is blue, and that V has at least one blue child. Of course, if V didn't have any blue child, then P1 will get stuck in the very first round, and therefore P1 will lose the game. But that's not what you want. You want NW1B, so P1 has to win the game. So therefore, oh, now my video is gone. Sorry about that. So V has at least one blue child, first of all, and at least one of its blue children has to be such that if P1 moves the token from V to U, and now you forget about this particular round of the game that has just been concluded. Now you sort of think of the game as beginning from the second round. So now it's P2's turn to move, right? And P2 has to lose the game, and she has to lose the game in less than n rounds. Why less than n rounds? Because the total number of rounds in the game has to be less than n plus 1. One round has already been played by P1. You are looking from the second round onward, and therefore P2 has to lose the game in less than n rounds. And so that's why P1 should be able to move the token to a vertex U, a child U of V, which is in the set NL2B superscript n. Okay, so this is how I set up the recursions. And so how does this help us in getting the probability small nW1B superscript n plus 1? So here you can see that I'm summing over. So basically, I'm summing over the number of blue children and the number of red children. So M1 is the number of blue children of the vertex V. M2 is the number of red children of the vertex V. Notice that the summation for M1 begins with 1 because V needs to have at least one blue child, else P1 cannot win the game. Chi sub B M1 comma M2 gives you the probability that V has M1 blue children and M2 red children. And this part, this expression gives you the probability that at least one of the blue children is in the class NL2B superscript n. Okay, so this is what the probability gives you. Okay, so this, this 1 minus NL2B superscript n whole to the power M1 is the probability that none of the blue children actually belongs to this class. And then you subtract it from 1 to 2, get the probability that at least one of the blue children of V has to belong to this class. Okay, so now when you simplify this, or rather, just do a bunch of computations, it just gives you this expression. So here you can see why I introduced these notations. Okay, so because otherwise, I would have to write GB of 1 minus NL2B superscript n comma 1. Okay, which is kind of annoying to write. So that's why I introduced these notations, and this is what you end up with. Okay, so likewise, you can argue that when you consider NW1 or n plus 1 or n plus 1, you end up with 1 minus GR2. So basically, it's all symmetric. So here you have GB1, here you will end up with GR2, 1 minus NL2RN. So here you had NL2BN, here you will have NL2RN. So this is how you find the recursion for a set of this form, NW1B n plus 1. Similarly, if you considered NW2B n plus 1 or NW2R n plus 1, the argument will be similar. You just have to keep in mind that in that case, P2 is playing the first round of the game, and that P2 is allowed to move the token along non-monochromatic edges. Okay. So in the next slide, I just tell you how we go about finding the recursion for a set of this form when you're looking at a losing set, NL1B n plus 1. So here, this means that if you place the token at V, and if you let P1 play the first round of the game, then P1 loses the game, and she loses the game in less than n plus 1 rounds, okay? So when will V belong to this class? First of all, the color of V has to be blue. Secondly, either V has no blue child, because if V has no blue child, then P1 of course cannot make any move, because P1 has to move from a blue vertex to a blue vertex, so P1 will lose the game. Or V does have blue children, but each of these blue children are problematic for P1. Why? Because if you go, let's say U is a blue child of V, once P1 moves the token from V to U, now again, forget about this particular round and sort of imagine the game beginning from the second round. And now P2 is the one who's playing this round, and P2 has to be able to win the game from this round onward, and she has to be able to win the game in less than n rounds, okay? So this means that each blue child, if V does have any blue child, then each blue child U of V has to belong to this class, NW2B superscript n, okay? Because there you can ensure that P2 starting from the second round will win the game, okay, and win the game in less than n rounds. So here, when you write down the recursion for the probability small NL1B superscript n plus 1, you have two terms. The first term gives you the probability that the blue vertex V has no blue child at all, okay? And in the second term gives you the probability of this remaining part of the statement. That is, yes, V has at least one blue child, but each of those blue children has to be in the class capital NW2B superscript n, okay? So now if you simplify these two or combine these two terms and then simplify them, you end up with this term. So again, you can see that, I'm making use of this notation. So this notation it really keeps coming back. Okay, so likewise, you can argue for NL1R n plus 1. So you can see the contrast between this argument and this argument. At least the contrast that stands out for me is that here it was okay for you to have at least one blue child U such that it belongs to this class, okay? Because here P1 has the P1 is winning, and so she just needs one avenue to win. On the other hand, here you have to make sure that each blue child of V is in this class, because here you're forcing P1 to lose, and so P1 has to be forced to move to a problematic vertex in the first round. Okay? So that's just a contrast that I wanted to point out. And okay, so this is kind of an ugly slide, but I wanted to include it just for the sake of correctness, mathematical correctness. You don't have to remember any of these expressions, but you can get 8 recursions like I showed in the previous 2 slides, and then you can combine them, and then you can come up with these 4-step, rather horrid looking expressions. So you can see that NW1B n plus 4 gets connected with NW1B n via this really long expression, this composition of several functions. So you can define this function h1, which is basically this function applied to x. And similarly for NW2B, you have again this 4-step recursion. So you can see that NW2B n plus 4 is related to NW2B n via this function. Again, you define this function h2. And now the key thing is that the key takeaway message from this slide is that if you let n go to infinity on both sides, you can see that this is going to go to NW1B. This is from one of the previous propositions that I showed you, that NW1BN increases to NW1B. So NW1B n plus 4 will increase to NW1B. On the right side, you can see that NW1BN will also increase to NW1B, and these are continuous functions. So the composition of this whole thing is going to go up to basically this function applied to NW1B. So basically, after you take the limit as n goes to infinity, you conclude that NW1B is a fixed point of h1. Okay, that is the takeaway message. This function h1, NW1B will be a fixed point of that. And that's how you can analyze what NW1B will be like. Okay, but of course, h1 is not a pleasant function. I admit that. Similarly, you can show that NW2B, again, if you take limits as n goes to infinity on both sides of this equation, you find that NW2B will be a fixed point of h2. Not only that, we can actually find out which fixed points these are in case H1 and H2 have non-unique fixed points. And that is by just looking at the behavior of H1 and H2, you can show that H1 and H2 are both monotonically increasing. It's easy to see if you just remember that each of these functions, GB1, GB2, GR2, GR1, these are all increasing functions, okay? And therefore, H1 and H2 will be monotonically increasing, okay? Now, how can you write NW1B? So NW1B can be written as limit as n goes to infinity of NW1B superscript 4n. I'm writing 4n deliberately, okay? I could have written n, that would have been equally true, but I'm writing 4n because in the previous slide, I showed you that I get a 4-step recursion. That's why I'm writing 4n. And so you can, this thing, by using the recursion in the previous slide, you can write as, is the same as limit as n goes to infinity of h1 n, this is the n-step composition, the n-fold composition of h1, applied to nw1b0, okay? So when you start with nw1b0 and you apply h1 once, you get to nw1b4. Then when you apply h1 again, you get to nw1b8, and so on you continue. So that's why when you consider nw1b4n, all you have to do is apply the n-fold composition of h1 to nw1b0. But nw1b0 by our convention is 0, okay? So that's why this is equivalent to writing limit as n goes to infinity of the n-fold composition of h1 applied to 0. And this tells you that actually nw1b is not just any fixed point of h1, it's going to be the minimum fixed point of h1, okay? So h1 is the function that goes from 0, 1 to 0, 1. And if you just restrict yourself to this set, then nw1b is going to be the minimum fixed point of h1. Likewise, you can do the same thing for nw2b. You can show that nw2b is limit as n goes to infinity of the n-fold composition of h2 applied to 0. And that's why, because h2 is monotonically increasing just like h1, nw2b will be the minimum fixed point of h2. Okay? So this is how you characterize what these probabilities are going to be like. And you can do same things for, you know, the other, so nw1r, nw2r, and so on. Okay? So this sort of brings me to the end of discussion of just normal games. We will go back to normal games later on, but now I want to focus on misere games. And I'm not sure, you know, please feel free to give me feedback as to whether this sort of color coding is actually helpful or disturbing for the viewers. Okay, so please feel free to let me know. I tried to color code according to the color of the vertices, and the subsets are exactly the same. You define them in the same way. You just replace n by m because now we are looking at misere games. Okay, so and the only new thing in this slide is that I define just a few notations. Again, these are for the sake of brevity when I write down, you know, complicated mathematical expressions later on. So P sub B is the probability that a blue vertex has no blue child, okay, which is also equal to GB superscript 1 of 0. So you can just write this down and find out that this equals this. P sub R is the probability that a blue vertex has no red child. Q sub B is the probability that a red vertex has no blue child, and Q sub R is the probability that a red vertex has no red child. Okay, so PB, PR, QB, QR. Again, if you forget these notations, please let me know and I'll recall them for you. Again, let me go through the recursions a little bit. I really enjoy writing down these recursions, I will be honest. And the recursion here is a little bit different because here the winning rule is different. Here you win if you fail to make a move, right? So when you consider MW1B n plus 1, again, this is a set where if you place a token at a vertex in this set and you let P1 play the first round of the game, P1 wins the game and P1 wins it in less than n plus 1 rounds. So first of all, because it's MW1B n plus 1, so the color of the vertex V has to be blue. And P1 will win the game if either V has no blue child, in which case P1 is unable to make even the very first move, so P1 wins the game because it's a misere game and not normal, or once again, it has some blue children, but at least one of these blue children is in ML2BN. Again, because if you consider a vertex in ML2BN, then that means that if P2 plays the first round, then P2 loses in less than n rounds. So this part is similar to the normal game, this argument, but this part is new. Okay, so that either V has no blue child. This is not allowed in normal, because in normal, if V doesn't have a blue child, then P1 will end up losing the game. Okay, so now using this relationship between MW1BN plus 1 and ML2BN, you can write this recursion relation. So when you consider the probability, so this is the probability of the root belonging to capital MW1BN plus 1 conditioned on the root being blue. So this first term is the contribution from this first part, that V has no blue child. And this term is the contribution from the remaining part, where V has at least one blue child, but then at least one of these blue children is in ML2BN. Okay, so when you combine these things, you end up with this expression. So this expression is pretty similar to what we saw in the normal games, but you have this additional term here. Okay, so this is where we make use of the notations PB, PR, QB, QR. When you consider ML1BN plus 1, so here P1 will lose the game if she begins the game. So here, first of all, V has to be blue again. V has to have at least one blue child, because if we didn't have a blue child, P1 will not be able to make the first move and P1 will win the game, but we want P1 to lose the game. So V has at least one blue child, and each blue child, so once again, you have to force force P1 to move the token to a problematic child of V, which means that each blue child of V has to be in MW2BN, okay? Which means that if P2 plays the first round, then P2 wins the game in less than n rounds. So again, using this relationship between ML1B and MW2B, you get this relation. So this is the small ML1BN plus 1 is the probability of the root belonging to capital ML1BN plus 1 conditioned on the root being blue. So you can see again that when I take the summation over M1, so M1 is the number of blue children of the vertex V, the summation starts from 1 because I have to ensure that V has at least one blue child. M2 can vary from 0 to infinity, and here this part tells you that each blue child of V has to be in the set MW2BN. Okay, so when you simplify this, you end up with this expression. So again, this part is the part which was not present in the normal situation, but here it is present. Okay, so and you can find the remaining 6 recursions in the same manner. And once again, this is the ugly slide, where again the takeaway message is that you can get MW1B and MW2B as fixed points of certain functions. Okay, the functions look ugly. They're composition of several, of these PGFs, but at least you have a function such that you can write MW1B and MW2B as fixed points of these functions. Okay, so and again, you get these 4-step recursions. You just sit down and just write down these recursions. So, and once again, these functions capital F1 and capital F2 are monotonically increasing, and in the exact same manner, you can conclude that MW1B will be the minimum fixed point of capital F1 in 0, 1, of course, and MW2B will be the minimum fixed point of capital F2 in 0, 1. Okay, so it's not just n fixed point, but the minimum fixed points. Okay, so at this point, I have shown the analysis of of the normal and misere probabilities. I don't know how much time I have. How much time do I have?
Something like 20 minutes.
Okay, that's good. So now, in the original, the Martin Holroyd paper, or Holroyd-Martin paper, they also come up with a bunch of inequalities. So I just want to quickly show you that the paper. So if you go to this paper, you see that you have this theorem, which has a bunch of inequalities. And the thing is, whereas these inequalities in part 1 and the inequality in part 2, these hold in general for my situation. The other inequalities, I could not show that they hold in general. In fact, I don't think they hold in general for my situation. So I'm still working through these. And also, there is this proposition, and I'm going to show you these inequality understandings a little bit now. That will be my next goal, and I'll come back and contrast things with this paper. So let me go back to full screen mode. So I compare the normal and the misere games on a few different trees. So in their paper, they don't, in general, they don't have to make any such assumption about what the offspring distribution is like, because they get these general inequalities, but I can't seem to get them. So I was analyzing the normal probabilities versus the misere probabilities on a few, typical Galton-Watson trees. So the first one that I look at is the Poisson tree. Again, this is the Poisson bitype tree or multi-type tree. So what is the Poisson bitype Galton-Watson tree? So in this case, every vertex will have a total number of children, which is Poisson lambda. So lambda is some given parameter. However, after that comes the, the bitype bar. So how do I define that? So conditioned on the parent vertex being blue, each child of V independently will be blue with probability pi sub B, and it will be red with probability pi sub R. Okay, so pi sub B plus pi sub R is equal to 1. Similarly, conditioned on the parent vertex B being red, each child of V independently will be blue with probability nu sub B, and it will be red with probability nu sub R. Okay, so this is happening independently over all the children of V. Now, if you use Poisson thinning, which is a pretty standard thing and a pretty nice property of Poisson distributions, then you will be able to say that this means that if X sub V is the number of blue children of V and Y sub V is the number of red children of V, then conditioned on V being blue, X sub V is Poisson with parameter lambda times pi sub B. So you can see that this has been thinned by the probability pi sub B. Okay, and similarly, Y sub B is Poisson with probability lambda times pi sub R. Again, it has been thinned by the probability pi sub R. And perhaps most importantly, X sub B and Y sub B are independent. Okay. Similarly, conditioned on the vertex being red, X sub B will be also Poisson with parameter lambda nu times B. Sorry, lambda times nu sub B. Y sub B will be Poisson with probability lambda times nu sub R, and X sub B and Y sub B will be independent. Okay, so this is sort of a very nice thing about Poisson that I wanted to exploit. Okay. Again, in the next slide, there will be some ugly expressions, but you don't have to focus on the technical part of it. I just wanted to write these down to show you, how I derive the inequalities that I do derive in this slide. Okay, so the idea will be to compare. The idea of this slide is to compare MW1B with NW1B. So that is the probability of player 1, P1, winning the game if she begins the game in the normal case versus the misere case. And similarly, MW1R and NW1R, okay? And the way I go about it is that, so first of all, NW1B 0, NW1R 0, MW1B 0, and MW1R 0, these are all 0 because the corresponding subsets are all empty sets. That's our convention. So we begin with all these values to be 0, and now we will perform a two-step recursion. So that's why I wanted to write down these expressions, but don't go into the details of these expressions because these expressions are nothing new. It's not like it's something innovative. It's just that in the previous recursions, the general recursions, I have just plugged in the PGF expression for Poisson. That's all I have done. So you can see here the two-step recursion, which relates NW1B n plus 4 with NW1R n plus 2. So you can ask me, why not consider the four-step recursion, which connects NW1B n plus 4 with NW1B n? And the honest answer there is that it becomes too unwieldy for me to be able to do any analysis there. So that's why I'm considering these two-step recursions. So connecting NW1B n plus 4 with NW1R n plus 2. Again, when you come here, you see that I'm connecting NW1R n plus 2 with NW1B n, okay? And similarly, I do this for the misere games. And now the idea is that you can see that we begin with all the 0 values. So they're all equal, they're all 0. And now I sort of inductively show, so this is why you get something like this that I will come and explain in a few seconds. I want to inductively show that NW1B n is greater than or equal to MW1Bn for each n, and NW1Rn is greater than or equal to MW1Rn for each n under certain conditions. And what I end up doing is that I subtract this expression from this expression and then try to see, just by using like calculus and just understanding the behavior of the function that I get, under what conditions will this minus this be greater than or equal to 0, under the assumption that NW1 or n plus 2 is already greater than MW1 or n plus 2. Because I say this is inductive, okay? So that's why I want to emphasize that this is inductive. So you assume that NW1 or n plus 2 is greater than or equal to MW1 or n plus 2, and then try to find the condition under which NW1B n plus 4 will be greater than or equal to MW1B n plus 4. Okay, so when I performed these computations, I found out that a sufficient condition for these inequalities to hold would be if this condition held, and if this condition held simultaneously. It's important that these conditions hold simultaneously. Then we will be able to say that actually NW1B, I write 2n, but it's just because I have two-step recursions. I'm pretty sure this is also going to hold for the odd indices. Anyway, so NW1B2n will be greater than or equal to MW1B2n, and NW1R2n is greater than or equal to MW1R2n. Now, there are two drawbacks to this result, and I want to point that out in case anyone can improve. The first thing is that I don't know if this sufficient, this is a necessary condition. I don't think so. I think that necessary conditions could be made much tighter. So, of course, there is a possible improvement here, but also because I'm using these two-step recursions, these two conditions are sort of tied together in that I have to have both these conditions to hold for this inductive argument to go through and for both these inequalities to hold. So it's not like I can simply say, oh, this inequality holds if this inequality holds, and this inequality holds if this inequality holds. I cannot say that. I have to tie the two things together, which to me is kind of, not very satisfying. So there is room for improvement. So ultimately, when you take the limit as n goes to infinity, you end up with the result that if these two conditions both hold, then we have NW1B greater than or equal to MW1B and NW1R greater than or equal to MW1R. Okay, so that's the final takeaway message from this slide. And I can come back and explain if you have more questions on this. Okay, I do an exactly similar analysis for binary trees. So what are binary trees? Again, it seems like a very standard model to consider, and so I went into the analysis of this one, just like the Poisson case. So here, each vertex can have either no child or two children. Okay, so if a vertex is blue, then it has no child with probability P0. It has one red and one blue child with probability P sub BR, two blue children with probability P sub BB, and two red children with probability P sub RR. Similarly, if you condition on the vertex V being red, then V has no child with probability Q sub 0, one red and one blue child with probability Q sub BR, two blue children with probability Q sub BB, and two red children with probability Q sub RR. Okay, so the only difference here is that I'm using P here and I'm using Q here, that's all. And once again, here I find that if both these conditions hold, if both these inequalities hold, then I'm able to conclude that NW1B2n will be greater than or equal to MW1B2n, and NW1R2n will be greater than or equal to MW1R2n. And again, when you take this limit as n goes to infinity, you end up with these two inequalities. So once again, the same problem remains that I cannot separate these conditions. I have to have both these conditions to hold for the inductive argument to work out and for these two conditions to hold simultaneously. So I cannot say that if the blue condition holds, then the blue result holds, and if the red condition holds, then the red result holds. I cannot say that. Okay, so there is room for improvement here. Okay, so the final slide, or the penultimate slide. So this is where I again want to show you this their paper. This is corresponding to their proposition 3. And they have a really nice proposition here. So the first item that you see, let's just focus on the first item. The other two I haven't included in the slides. So again, they consider binary branching, which is similar to the situation that I just talked about. So every vertex has either 0 children or 2 children. And in this binary branching, they show that the normal game, you can define draw probabilities for the normal and misere games, right? So for the normal game, there is a phase transition for the draw probability. Okay, and it tells you that when the probabilities are given by this 1 minus t comma 0 comma t, so this is the probability vector. When t exceeds a certain threshold, the probability of draw becomes positive. And you have a similar misere draw probability phase transition as well. So you get these continuous phase transitions. My result is so stark contrast to this. And I found that when I analyzed the binary trees for my situation, there is no phase transition. Basically, what I end up getting is the following. So in these couple of lines, I just defined the draw probability. So there is nothing new going on here. The only situation where I have a positive draw probability and the probability is 1 is when P sub BR and Q sub BR are both 1. What does that tell you? That tells you that every blue vertex will have with probability 1 blue child and 1 red child, and every red vertex will have with probability 1 blue child and 1 red child, which basically means that you have this really, like a symmetric tree, and you just, no matter which player you consider and whichever vertex that player is playing on, she always has a move, because every blue vertex has 1 red and 1 blue child, every red vertex has 1 blue and 1 red child. So there is no point in the game where the 2 players can get stuck. And so this definitely leads to a draw. The game can continue forever. So it's almost like, I don't know if I should say this, but it's almost like a 0-1 law. So in their case, they have this nice continuous phase transition. But in my case, I find that in any other situation, the draw probabilities are all 0. So, and the same thing holds for the misere games as well. That only in the situation where PBR and QBR are both 1 and all the other probabilities are 0, you have draw probability equal to 1. In all other situations, the draw probability is 0. So this is to me, quite a stark contrast with their result. And I'm trying to analyze the same thing for the Poisson situation. So because, in the second point, they have the analysis for the Poisson case. And I'm trying to go through that right now. But the computations are far more complicated than in the binary branching case. Okay, so this is all that I have to say. And I'm hoping that, I was able to express everything clearly, because, this is not a face-to-face talk. And yeah, so this is my most favorite slide. So I'm always very proud to show this slide to everyone that I found, So yeah, go ahead. And if you have any questions, please.
So thank you, Moumanti, and I would ask everyone to unmute themselves.
Thank you.
Thank you.
Yeah. Thank you.
Any questions?
Yes, Monty, thanks for a wonderful talk. Can you go back to slide 6?
Yes, let me see if this works. Yes, this?
Right, that's the one. So, I mean, if you go down to the consequence, which of course is one of several similar consequences,
Yes.
but I'll ask my somewhat standard question. Can you say something about about how quickly it goes to a limit? Or to put it another way, what can you say about the probability that there's a win, but there's not a quick win? The win has to take more than n terms. Can you say something?
And you're hoping for some sort of exponential behavior here?
Well, that would be nice, yes.
Yeah, but so one of the sorry, one of the problems is that beyond understanding that these probabilities come as fixed points, I'm not too sure I can, if let me go to this slide, and then if I analyze this, if I can analyze the behavior of this, perhaps I can say, how fast this is going off to NW1B. But to be very honest, I find it quite unwieldy. So I haven't tried that. But this is a question that I'm actually, thank you for suggesting it,
Okay.
because I would really want to look into that. But I feel like maybe I have to make some assumptions about the offspring distribution, and then because otherwise I'm not sure I can say much. Yeah.
I mean, it's possible that there would be some results for some of the particular types that you've already discussed.
Right. I mean, even something like this is something like this is not that easy to analyze. So even when I have an explicit expression for the recursion relation, or how do you call it, generating function and stuff like that. So but yeah, it would be really nice to find out. I know that we are like large deviation people, so we will definitely, that's a good question. Yeah, thank you for that.
You should tell everyone about your new position starting in January, which you did.
Oh, okay. Yeah, I was telling Hansa, but yeah, I'm starting in, so the institute is known as Indian Institute of Science, Education and Research, and it's in Pune. So Pune is a city close to Mumbai. It's in the western part of India. It's going to be a tenure track position. So I also don't know if he will continue with me, but one of the attendants is Dhruv. I don't, maybe he disappeared. I'm not sure. So Dhruv, maybe you can turn on the mic and say hi to everybody. So hopefully he will be my PhD student, and we are hoping to work together on exciting problems. So I don't know if yeah. So
hello, Dhruv.
Yeah. So, and any other question?
Well, I hope, Dhruv, that you will become my grandson.
Academic grandson, yes.
I already have one Indian grandson, and I would like to have another one.
So, Moumanti, I missed a couple of minutes of the beginning of your talk, which might have had some critical points about motivation and stuff.
Yeah. So you mean in the first slide, or?
So let me ask you a question. So the definition of your game, and where one player follows monochromatic edges and the other non-monochromatic. So I wondered at first why you didn't just have a player called blue who plays to blue points and a player called red who plays to red points. But actually,
I see.
Looking at it looks like that's actually equivalent.
Is it? I mean, you mean from any vertex, the player goes to a blue vertex, and from any vertex, the other player goes to a red vertex.
That's right, but I think that's equivalent if you switch around the distributions.
Actually, I didn't think of that. Thank you for, both of you. Thanks for suggesting new questions that I can take a look at.
It might be worth noting that. I think part of Ander and James's motivation in writing their paper was to try to understand to make a model for random games and find out what happens in it, so that I can answer questions. What happens with draw probabilities and are you more likely?
So when you say random games, you mean the setting is it's sort of randomly unfolding in front of them, or is it something that is being generated?
No, I don't mean that. So
okay.
Their game and your game are what we would call a quenched game. So the random,
yes, not annealed. Yes, yeah.
Right,
yeah.
and then everybody sees the board.
Yes.
So and their paper they have basically a model for a random impartial game. And so your model may be could be motivated by the idea of making a random partisan game.
Okay.
In which case you would want to say, okay, in a position in a random game, then the blue player can make certain moves and the red player can make certain moves. And of course, in many actual games, the overlap. So in your, in other words, a move made by a blue player, the same position as a move made by the red player. So your model, in a way, is a model of games where that doesn't happen. So there's no overlap.
Right. Right. So, if it turns out to be, like you say that maybe they're equivalent, but if they don't turn out to be the equivalent, that will be the subject matter of my next paper. So
that's right. It's actually be a good thing for you if they're not equivalent, but I think they probably are. Yeah.
Okay.
Right. So the idea is that when suppose you're player one in your game, right? You're trying to follow a monochromatic edge. So suppose that right, so you're trying to go to a blue point if you're at a blue point.
Yeah.
Red point if you're at a red point.
Right.
So if you just take the distribution for red and blue children for one of your colors and flip it, you should get the model. You can check that out.
Okay. So when you say flip it, you mean like sort of like this thing is going to become chi sub b of n comma m, something like that?
Yep. Yeah.
Okay.
I think that's all you need to do.
Okay. Yeah, I would like to check that out. And then,
Joel is nodding his head. That's a good sign.
Yeah. Okay. Okay.
But of course, could be much more general too. I mean, you could have.
The paper. So in the paper, I actually was, considering. So for each color J, there is a subset of colors Sj, such that the player one is allowed to move the token from a vertex of color J to a child whose color is in Sj. That's basically what I was considering, and so that sort of generalizes this. Yeah,
that you could certainly do. But here's another suggestion, Moumanti.
Yeah, go ahead. Yeah.
Keep it at add just one color green. Okay. This would be probably what a Berlekamp-Conway and Guy would think of first, based on their way of developing things. So, go to the red-blue game that I was describing before, which we think is equivalent. Now add a third color green, which can be played by either player.
Okay, I see.
So that corresponds to the rules for Hackenbush, or one of these famous games developed by Berlekamp, Conway, and Guy.
Okay, so you were saying that each of the players can move to a green vertex, no restriction, but for the first player, it can move to a blue vertex and not a red, and the second player can move to a red vertex, not a blue.
Exactly.
Okay.
Yeah, see what you can do. You've got.
Okay, thank you for suggesting these problems. I'm writing them down.
All right.